So this is a talk that's supposed to be about the future of the microscopy suite as it has to do with Beckman, as it has to do with the rest of the university. And so what I want to do is I want to talk about some instruments that we've acquired recently and not really advertised. I want to talk about some brand new instruments that we have. And I also want to talk about a couple of things that we're going to be getting in the future. So in the title slide with the Blade Runner font on it is a kind of a cool idea that Travis's group had put together for the future of the Beckman atrium. There were a bunch of different concepts for that. So we'll just go ahead and go. So the imaging technology group is part of the Beckman Institute, and the imaging technology group is basically has always been the Viz Lab and the microscopy suite. But if we kind of expand that a little bit, we have the Viz Lab studio downstairs now with the 21-foot ceilings, and where Travis can hang all of his camera devices and things like that. And then also another part of the Viz Lab that isn't always in the building but is always available is the ITG graphics group. And so I think that the Viz Lab is really important. One of the things about the Viz Lab studio being down in the basement right in the middle of the microscopy suite is that that means people are going by the microscopes all the time. Travis is doing macro photography. Travis is doing super ultra high speed photography. And what happens is it means that with Travis downstairs, there's more interaction between the Viz Lab and the microscopy suite, and I think that's really cool. So the Viz Lab with the poster covers of some of the journal covers that they've done for so many years, a really cool thing to do, and then all the super high-end microscopes. So I took this picture on Saturday or Sunday. And then the Viz Lab studio.
Nobody's there. Yeah. Is that what you're trying to say?
That's what I was trying to say. And nobody's in the Viz Lab studio either. Nobody's in any of these pictures. So the Viz Lab studio, you can see the 3D scanner in there. You can see this like really funny looking camera right here with the little pointy beak on it. That's a 2 million frame per second color TV rate camera, and that was purchased at the same time that Phil Anderson got the same camera in black and white so that they can do sort of XZ imaging if they want to. And so that's the trap jaw ant people. That's the people who went to Duke to borrow a camera, and we said, well, we can't have that. We need to have our own. So we have a 2 million frame per second camera. And then we also have 3D scanning, which is what this little box is right here. And that's the one that was used to image the alma mater when the alma mater was being taken apart for cleaning, so that people could get their picture taken with the virtual alma mater. So what happens is people are often asking Travis, well, do you have like a smaller scale 3D scanner? And actually it turns out that we do. And so this is one of the things where we profited from having Travis downstairs. This stylus profilometer functions as a angstrom and nanometer and micron scale 3D scanner. So this is where we took a 10-cent euro coin and with Botticelli's Venus on it, and went ahead and got a high resolution image of it. So I think that sometimes what we have to do is sort of advertise these things a little bit, and so that's part of what I want to do today. In the microscopy suite itself, we have generally 4 different modes of collecting images. So we have light and laser microscopy. Microscopy in that level is almost always fluorescence now, as you know. And then associated spectroscopies, so mostly Raman spectroscopy, but we have UV vis, near IR, those kind of things. One thing that I point out sometimes is that the Bargov lab, one of the Bargov extensions of the Bargov lab is downstairs, just past some of our instrumentation, and they have FTIR and nonlinear Raman and things like that. And so when we get someone who's interested in FTIR, we have an agreement with Rohit, and we can forward people to the Bargov lab to do FTIR. So I really like those kind of interactions as well. So we also have scan probe microscopy, but not very much. We have a really nice AFM, and the stylus profilometry also fits under scan probe. But we know as well that over at MRL you have every flavor and version of AFM, and so we don't want to try to copy these things. And even IGB has a cipher AFM that you can control underwater, so under liquid. So I'm sure that MRL does as well. So another part of the emphasis that I would like to make is that Beckman is part of the greater research university, research in the university. So you have MRL, you have IGB, you have the ITG that we're part of, and then you have other scattered facilities like the mass spec and different things like that. So what Glenn Freed and Morrow and I meet every once in a while, and don't really argue about things so much, but we do make each other aware of the instrumentation that we have, so that we don't have big overlaps. There's certainly going to be some overlaps. And we have scanning and transmission electron microscopy. We have a really nice new environmental scanning electron microscope that I'll show you a little bit more of later. And then we have an antique TEM that's like really, really beautiful space age looking microscope when the space age was in the 60s. And then we have almost all the sample prep kind of stuff that you would need. So what we do is we focus a lot on bio. So we want to be able to be really versant in bio, really versant in biomaterials, and then we're always going to pick up some material samples. Sometimes because we have eSIM, so we can do wet SEM, so we can people can look and see contact angles in real time, cause water to show up on their samples. And then I want to sort of move into the order of what we have and show you some of the new things. So this is actually the Leica SP8 confocal microscope when it was brand new. You have 4 companies, Olympus, Nikon, Zeiss, and Leica. Leica has a really nice instrument, really bad service, but a really nice instrument. And so we've learned how to deal with Leica. Dan Nguyen is really good at dealing with them. He's in charge of way, way more instruments than I can even talk about today, and does a great job. And we've, as I said, I believe we've learned how to deal very well with Leica, and we actually, I'm saying that their service is bad, but it's been really good for the past couple of years, which is a big deal. So this is when we had it set up in the other room, and then we moved it into our biosafety level 2 space, what we had made our old clean room into a biosafety level 2 compatible space, so that we are able to bring in cell lines that you just normally can't carry around with you. And I wanted a confocal image. Dan Nguyen put something together for me yesterday afternoon, so this is taken using that confocal. And one of the things that it shows is that The Leica SP8 quietly is very, very good at tiling. So, so I used to talk a lot about how the Zeiss was so good at tiling that we quit writing our own software to do tiling. But actually, Leica is just fantastic. So this image right here on the left, about 150 microns wide, is actually way down here in the corner, and it's all been tiled together, and it looks really nice. According to me, but I think it does look really super nice. So the Leica SP8 is a really nice workhorse microscope. The other thing about Leica is that they have a patented means of getting 5 laser lines out of the microscope, and so 5 biological laser lines. So that's a trick that the other confocal, the other 3 manufacturers are not able to do. They're protected from that by Leica patents. One of the cool things that we have since we moved the Leica SP8 into the BL2 space, the cell and tissue culture facility, and we have that set up so we can take microscopes out and put microscopes in depending on who has what and what kind of conditions they need to work under. But one of the really cool things is you notice that the Leica didn't have a great big enclosure around it for CO2. And so what we did was we found out about Ocolabs, and Ocolabs, you can have these little tiny enclosures that sit on top of your stage. You can hook them up so that you can feed the CO2 into the cells. You can heat the cells the minimal amount that they need to be 37°C to keep them alive. And the other thing is that you can also buy these incubators, and you can have different connections to them. So some people want to come in and do electrophysiology, and they want to drill little holes in this, and I said no, but you can certainly buy your own little incubator, and we have all the things that you need to connect it to so that you can do electrophysiology or something like that. So I think that it's really a kind of a cool thing. The other thing that I put on my slide so I wouldn't forget is that we added resonance scanning capability to the Leica so that you can do TV rate imaging. And then one of the things that we do that we don't normally do is kind of experiment and build an experimental system. And so more than a few years ago now, Jeff Moore wrote an MRI proposal for a confocal Raman imaging system, and we had a couple of ringers on our team to write all the specs for this, and we put together what I think is a really, really nice confocal Raman imaging system based on an Olympus microscope. It didn't come this way, but now it has 405, 532, 633, 785, and 830. And because the company who produced the bid wanted it really bad and woefully underbid, we were able to buy all kinds of extra stuff for it. So we have a tensile compression stage, which also fits inside the SEM. We have heavy duty stage. We have the last graduate student we were working with from Mary Craft's laboratory wanted a 63x long working distance water immersion objective. It's kind of a rare beast. We were just able to buy that outright. So we have what I think is a really, really nice confocal Raman system. One of the things that Deanne Nguyen is not entirely happy about is that it's hooked. It doesn't have fiber-coupled lasers, but I think that if you run a laboratory where people are going to be working in the middle of the night and want to change lasers in the middle of the night, it's just not a good idea to have somebody yank the fiber coupling out and try to plug it into something else. It's not going to work. So these are all free space lasers, which create a problem, but it means that people can change wavelengths whenever they want to. And so I'm talking about something that's not on the screen. So what happened is we wanted to still do better with our Raman spectroscopy, and so we got funding from Beckman to go ahead and build ourselves a deep UV system. And you can do 244, you can do 266. We got a 266 laser from Spectrophysics that has way more wattage than we need, is really nice. And Dianwen put this system together using an Olympus base, using a quartz objective that isn't even listed by Zeiss. So he bought this objective that's only for industry on eBay because you can't call Sam and tell him that you want this objective. And so he put together a really nice system. It has 532 so you can see what you're doing, and then 266 to go ahead and generate spectra. And so up here is one of our first spectra of calcium fluoride. So we're looking forward to having people who might be interested in using this. The idea of deep UV is that some bonds, like imide bonds, are in about the same energy realm as the wavelength itself, and so you're going to get a great big enhancement of the signal. And also the autofluorescence that you're still going to get is just further on down the spectrum, completely out of your way. So there are a lot of positives and negatives on this, but I think it's a really fun thing to have put together, and we'll see who has uses for it. I know that one group in Germany uses the deep UV to damage DNA, and then they use 532 to see what the damage was that they caused. So that wasn't really what we planned this for. Another thing, so something that's coming up, something that, so this photo was taken on Sunday, and it's already different now. They've already got all the furniture kind of set up on the right. So this is room B500E downstairs. When Dan Yano put together his proposal for an upright confocal with long working distance lasers where he can do rat and mouse live brain imaging and go at least a little bit more than a millimeter into the brain using these lasers, I decided that I didn't want to host that in the biosafety level 2 space because it just sounded like it was going to be too messy. And so thankfully Beckman let us go ahead and build this space. We tried to build a generic space because we don't know what's going to happen in the next 10 or 15 years, sort of the future of Beckman. But we need the lasers to come in. We have 5 giant pallets full of parts that are going to fill up this room, and so this little room right here is going to have the table in it. We've already got the table. We're going to set this system up, and there's going to be some audio experimentation, so we needed to have a soundproof room in there. So everything's coming together really nicely, and this was a grant proposal that had a whole bunch of really good heavy hitters on with really good experiments set up. So we're really excited, and we think maybe we're going to be up in January sometime with this system. So this isn't deep UV, it's deep IR, I guess, imaging. And so I clipped a little picture of the microscope up there, but the whole thing's going to have a big enclosure. It's going to be massively large. So I want to move to micro CT. So in 2006, we had a just under $2 million grant funded for X-radia, micro, biomicro, and nano CT systems. And the nano CT system was serial number 9. It really was one of the first systems out, and they learned a lot at our expense on that. But we're keeping our micro CT and our biomicro CT. The difference between these is it's not necessarily that you have to go bio with the one that we're calling biomicro. What it is the kV that are coming in. So when you want to look at a biological sample, you're going to back off on the energy so that you gain contrast again. So it works the same way that SEM works, same way that TEM works. So when you're using a TEM, you go to high kV to get really good resolution, but you need to back off to work with bio because you can't just, well, like with an SEM, if you get bad contrast, you can just dial it right back in. So the biomicro CT gives you a better range and a better low-end range of X-rays so that you can see the parts besides just bone. So you can see tissue, and you can see changes in tissue, and you can see the insides of lungs and things like that. And then this is a bat skull that I had up on the screen. You can see there's not really a bat skull inside the little CT machine. So what we're doing is we took our nano CT and we are prepared to give it away to Lingjun Ming, who is doing some really kind of cool X-ray fluorescence imaging and hopes to be able to do X-ray fluorescence in 3D, so 3D microscopy X-ray fluorescence. So we're sort of hoping to help him that way and not have this giant monstrous thing down there. And so we're getting, and these are some pictures. So Bruce Falk told me that he wasn't coming, so I should have just taken his slide off. But this is one of the things that we can do with micro CT is go ahead and get these images and partition these images however we want to, and then subject them to analysis. And so what's really cool about the Viz Lab is that all of these things can go upstairs. All of these 3D data sets can go upstairs and be subjected to almost any kind of analysis, finite element analysis, all the different kind of things that you might want to do because of the Viz Lab. So where all the super high-end computers are, all the really nice software that you wouldn't want, even a professor wouldn't want to purchase by him or herself generally. So everything is sort of in-house, and I'm really happy to be supporting X-ray microscopy. So we are getting 2 new X-ray microscopes, and we're getting another nano instrument. This comes from Rigaku, the Nano 3DX system. We're getting these 2 systems in December, and we're already very excited about it, and I believe as prepared as we're going to be for it. So this system, 270 nanometer resolution. It's not as good as our old nano CT, which had 50 nanometer resolution, but was almost worthless to try to use the way that it was set up. So 270 nanometer actually merges right with Glenn Fried's confocals. So and there's some purpose there because they do serial block face imaging. They have a whole array, and this is another sort of way that we work with the people all over campus as much as we know about what people are going to have. Glenn Fried over at IGB, we seed CEDE, we seed super resolution microscopy to Glenn Fried's group. So he's going to have ARIScan, he's going to have the $900,000 version of structured illumination microscopy, really, really nice high resolution imaging. He's going to have light sheet microscopy. He has a whole array of really nice confocal microscopes. And then it just happens that they did go ahead. Glenn always wanted serial block face microscopy. So this is an SEM that you have a sample that you've prepared in it, and inside the SEM is a microtome, and the microtome can shave off pieces of the sample. I thought that it was 15 nanometers at a time. They've told me it's more like 50 nanometers, but you can shave off pieces of the sample. You've heavily dosed your sample with osmium so that you'll get really good images, and so you can get 3D scans in this other way by slicing, imaging, slicing, imaging, slicing, imaging. And so what we see there is actually a way where we can help, because one of the things that I haven't mentioned yet is high pressure freezing freeze substitution, which is in some ways very comparable to what Glenn's able to do. So what I see is, because you're doing the kind of things that you're doing to your samples, if we can high pressure freeze Glenn's samples for him and go ahead and impregnate them with osmium and then have it so that they can go ahead and do their slices, instead of having a chemical fixation, which I'll show you one image of really soon. Instead of doing chemical fixation, you're freezing the samples in vitreous ice. You're freezing the samples at an incredibly high pressure, about 33,000 to 36,000 psi, so 300 some bar pressure, liquid nitrogen temperatures. You're freezing the ice so fast that the hydrogens don't have time to reorient themselves and stick together and make the kind of ice that we normally think of as ice. So when we can do that, and then we can keep our samples that way, and we can freeze substitute, we can bring the temperature up and infiltrate resins in there and do the various other things that we're doing, then we can do a really good prep. We have to work all of these things out. It's a horrible, miserable pain to do this kind of stuff, but the things that come out of it, I think, make it worth it. And so also I saw Mariana came in. One of the things that we haven't done is we haven't got our 5,000 Newton load frame yet. So I think of Mariana and Ivana Yashuk and a few other people, Amy Wagner Johnson, who would be interested in that. So I actually asked the Rigaku people if there was a possibility of putting one of those load frames in this system. But either way, I believe that the future, we're going to be able to get a killer heavy-duty load frame inside either our Biomicro CT or this instrument. What also is cool about Rigaku, so it's not like we just switched brands on purpose. Rigaku has a means of imaging that X-Radio did not have. And so I said, well, Lele, what is it? He says, well, we don't know yet. So it's a kind of a secret. And so I showed him some things. I made a slide today and I showed the setup, and I said, well, is it like this? Is it like this from this slide? We don't know yet what we're going to find out, how they do this kind of imaging that actually gives much better resolution to your 3D image. So we're very, very excited about this. Now this is like a headache in a box. So this is what we did. I wanted to test amber, because we have never been able to image amber samples very well with our micro CT system. So I sent an amber sample to Rigaku, and so they went ahead and did it. They did, I think, a really pretty good job. You can go right in through the mouth of this fly and go all the way through the fly and come out the ovipositor, I guess. But it gives me a big headache to watch it. And so I want to try to, I think that we can do a lot better. So I remember when they sent us this, and I was like, oh, I don't want to show this to anybody, and so I'm sorry, you guys, I had to take a look at it, but it's really exciting, and we actually have a guy over at the Natural History Survey who has 5-gallon buckets full of amber, and so we're really excited to try to fit him in. And so the other micro CT is quite different. So this one will be coming in December as well. And so this system, and sorry I have such poor quality images. These are the best images I could get. So anyway, what this one is, this little R2D2 looking like steampunk micro CT system. The X-rays go around the sample. There's a central gantry, and it has a fairly good diameter to it and open end, so I expect that we're going to be able to do some tensile studies. You can collect an image with the X-ray spinning around the sample. You can collect an image in as little as 8 seconds. And you can do the reconstruction supposedly in like 15 seconds. And so that is real, and 4.5 micron resolution. So that's 4.5 micron resolution is really not bad. It's like 2.5 bacteria long. It's just, I don't think it's really bad at all. And I'm really looking forward to what we can do with this. And then I have somebody else, in case nobody uses this instrument, which I think is unlikely. I have somebody from the Illinois Natural History Survey also who has about 12,000 birds that he wants to do micro CT on. So at 8 seconds a bird, it can just like stuff birds into it all day. So and he wanted to get a volume price for that, but I think that we actually have pretty good prices for this, so I wasn't going to give him a big discount. He's not going to be able to handle large birds. I went ahead and put the specs up on this. 240 millimeter scannable range, that's the length of the gantry, 72 millimeter field of view. I believe you can also stitch some of these images together. I'm not sure, maybe not with this kind. Lele says no. And then you can see resolution 45 microns. That's, I believe, is a typo. And because it's going right back if that's what it turns out to be. So I'm really excited about this, and we don't have a whole lot of information up, but we'll get it soon. eSIM, I want to highlight the new Quanta 450 FEG eSIM, even though it's a couple years old now. This is actually eSIM wet mode working as it was promised in the 90s. So it actually works now. You can look at non-conductive samples without getting big charge lines, without having those kind of problems. You can use water vapor as a cascade amplifier of secondary electrons. It works really, really nicely to give you your images. You can also, people say, well, dude, I don't want to use water vapor in my microscope, even though it's actually like less humidity than is probably in the air right now. But you can use nitrogen as a cascade amplifier of secondary electrons and get really beautiful images too. So this is actually and of course we just take pictures of bugs for something like this. But this is just a fantastic system, and it has a lot of things we haven't even used yet, like a stem detector inside it, and things like that. So we just like bugs, I think. And so this is Jim Nardi going through the leaf litter and asking Kate to take SEM images, which is a really good idea to have Kate do it. And so you can see this little orobatid mite in here, and you can see its cuticle, and then you can see that it has a kind of a net, where you can hardly see it. It has a kind of a network around its cuticle, and this is what it looks like up close. Really, really beautiful. And then you can see there's about 3 or 4 different kinds of species of bacteria hanging around on there. So it's just a super nice instrument for almost anything. This is from yesterday. So we had a guy who works in Sungwoo Nam's lab in mechanical science and engineering. He has these woven stainless steel. So the Hast alloy has a more nickel-based stainless steel. And so you can see the woven together components of the stainless steel, and then the reason that they look kind of grungy is because he's gone ahead and used CVD deposition of carbon nanotubes on there. And if he gets the carbon nanotubes clean enough, instead of getting big globs of graphene on there, which is more hydrophilic, then he'll have a hydrophobic sample. And so you can see this is just a time sequence where we have, Kate did this, we have water condensing on the surface of this, and by the time they were done, there was just like a great big puddle of water inside the SEM, which is fine with this SEM. You can see that Kate went up as high as more than 12 torr to do this. So you can get some idea of contact angle with this. When we've done contact angle in the past, sometimes we have to do a few tricks to be able to image those droplets from the side to get an idea of the contact angle. And these samples such as this are one thing they're using them for is to desalinate water. So there's I asked them about this. There's a variety of different things that it does. They kind of haven't settled on what it will do, but it's a kind of a cool thing. And this gives us an opportunity to show what wet mode looks like. This is a sore point, but with BugScope, we ran BugScope for 17 years on the old microscope. We still have to write the software, but we have a really good programmer now to rewrite the software for BugScope. BugScope is our K through 12 outreach program where kids anywhere in the world can send us bugs. We arrange to connect with their classroom at a specific time in Australia or in Shanghai or in Canada or Ireland, or we connected with some people down in Buenos Aires. They can control the electron microscope from their classroom, see what the images they're getting, and they can type questions to us. And so it's really, really super fun when BugScope is running. We just have this microscope that has this bizarro software, and it's really a little bit tricky to get the control of it. But now I'm on my third programmer, Ron Carbonari, who some of you might know. He's really, really good. He's done much more than the previous programmers just in about a week. So I'm really excited. I can't say when it's going to be back up again, but I'm really stoked to have that going. So TEM, Beth Etchison did a talk yesterday about TEM tips and tricks. So I don't think that's what TEM stands for, Travel and Expense Management System, so I had to spell it out. So with TEM we can do kind of like the normal stuff. So we can do negative staining with these liposomes. We can look at different kinds of nanoparticles just directly on samples. We can also do, and this is the point I want to make with this slide, which I do on a lot of tours, is if you had a microscope facility on your campus and you wanted everything that you had to pay for itself, you wouldn't have a TEM. A TEM is probably never going to pay for itself in service fees. And you might not have an AFM either. But I think that a hallmark of research university and a high-end research university like the University of Illinois is that we can do correlative microscopy that gives you these really good publications. We can say, okay, look at it this way, look at it this way. Here's the little polymer moieties on these proteins that Yang put together. Here's what it looks like in our TEM. And so it's very, very exciting to be able to do this kind of stuff. And when I go through the lab and I see all these pieces of equipment in there, if you wanted to make money, you'd have an SEM, maybe a micro CT, maybe a really nice Raman confocal, which gets used all the time, and one or two other instruments, and everything, maybe a regular confocal. The other instruments, I don't think that we should expect them to pay for themselves, but I think that they have an extended value in people being able to get good publications, correlative microscopy, bring in the grants, and really add to the prestige of the university. So this is another thing that we do with TEM is we started out making TEM holders. So the really finely machined part of the sample holder that goes into the TEM, and we had the nerve to try to have them machined ourselves. And so the first thing we did was we made a TEM holder with a nanomotor in it so that we could pull on samples, so that we could, for example, with Dr. Tahir Saif, when before he went bio, he was putting little 50 nanometer films in this pulling system, and we're able to move angstrom movement and tear the grains apart and image that while we were doing that. So once we had gone through all the pain of making a TEM holder with a nanomotor inside the barrel of it, we thought, okay, we can do this again. And so we went ahead and made an STM holder for the TEM with these just horribly painful measurements that don't ever seem to quite work out, but you just have to work and work until you get it right. So what we did on this TEM holder, we made it so that the barrel could be the same barrel, and we could just pull the tip off of it and make new tips for it. And so the first thing that we did was we made an STM tip holder for the lighting group so that they could do quality analysis on their STM tips, so they didn't have to just try their STM tip out and find out that it wasn't any good, that it was all curled up like a shepherd's crook. And then what happened out of this is they learned how to sharpen AFM tips actually and STM tips, and so we're seeing a no longer confidential slide of that where you can see the way that they've made this tungsten tip, and then you can see the tungsten tip has an oxide on it, so you could try to hit it with a big current and blow that oxide off, but that's not really the best thing to do. And so they actually have patented their own procedure for getting these fantastic radius of curvatures on AFM tips and STM tips, and it's really exciting. This one, the radius of curvature on the right is 4.2 nanometers. I saw one the other day that was 2 nanometers radius of curvature, so that's really, really cool. What you're trying to do, of course, is have a tip that just has like one atom at the end of it. And so I'm really excited to be able to help the lighting group and to be able to do this kind of stuff. So I kind of skipped one version of, and Kate was looking at my slides earlier, and she goes, well, where's the ultra-thin sectioning stuff? And so this is just a list of some of our stuff, most of which I'm not going to talk about, but we can see that there's 2 ultramicrotomes now. I took one ultramicrotome and had it refurbished, and it's really nice, super solid ultramicrotome. The other one we can actually do cryo on if we want to go and do cryo. And then a lot of people want to know what a diamond knife looks like, so I took a photo of a diamond knife sitting next to a nickel because they want to know what diamond knives are because they're so expensive. And so that's the sharp part of the diamond knife. This part back here is called the bode. It's not actually a very good picture, I'm sorry. And then I put it next to Jefferson nickel, where Jefferson has a mullet haircut, which is just kind of bizarre. So this is high pressure freezing, and high pressure freezing is like super, super loud, completely bombastic. You can hear the smash of this 33,000 PSI all through the lab, and it irks Ursula, because Ursula works with me on this. She's provided all the pictures that I have actually for high pressure freezing. And so this is what the system looks like. You can see that thing that looks like some kind of like a potato masher right there. That's actually the test holder, and then you put the normal holder in there when you're going to do high pressure freezing. It sticks like straight down in this chamber, and then this rod on the left goes through this hole right here in the holder, and when you hit the button and you have 33,000 PSI, that rod, the vertical element, keeps the sample holder from blowing right through the ceiling and embedding itself in the concrete of the floor above us.